The acid dissociation constant for benzenoic acid is 6.3 times 10 to the minus 5. Calculate the equilibrium concentrations of hydronium ion, benzoate, and benzenoic acid in the solution if the initial concentration of benzenoic acid is 0.05 molar. All right, so like any equilibrium concentrations we're trying to get to, right, we have a Ka value which tells us how far forward the reaction goes. For every X amount of benzenoic acid lost, I'm making X amount of its conjugate base and X amount of H plus ion. So X represents the H plus concentration. We can ignore the change in the initial concentration of benzenoic acid because the Ka is so small. We're not losing any significant amount, and solve for X. X is the H plus concentration, or the hydronium ion concentration. Also the conjugate base concentration. If I subtract that value from 0.05 molar, I get the concentration of benzenoic acid at equilibrium. Determine the pH of a solution of the following. Ka and Kb values are given in Appendix D. All right, so we had to look these up. 0.095 molar hypochlorous acid. All right, so I had to look up the Ka for hypochlorous acid. It's 3 times 10 to the minus 8. So this is a very weak acid. We're starting with a very low concentration, but for every X amount of hypochlorous acid I lose, it's going to be inconsequential to that initial concentration. So X will equal the H plus concentration. Again, I can ignore the amount of hypochlorous acid I'm losing. Solve for X. Take the negative log and get the pH. So these are just, Ka expressions are just equilibrium expressions. Solve for X, and that gives us the H plus concentration. Take the negative log, get the pH. For C, we've got hydroxylamine. Hydroxylamine is a base. Okay, so it's going to hydrolyze water to produce hydroxide ion. And for every X amount of the base I'm losing, I'm making X amount of its conjugate acid and X amount of hydroxide. So I'm, again, losing an inconsequential amount of my base. It's a very weak base. Solve for X. X is equal to the OH concentration. If I want to get the pH, right, I could do it two ways. I could plug into the Kw expression, divide this hydroxide concentration into 10 to the minus 14, and get the H plus concentration, then take the negative log and get the pH. Or I could take the POH, which is taking the negative log of the OH concentration. Once I have the POH, I could subtract it from 14. If you take the negative log of the H plus concentration, you get the pH. If you take the negative log of the OH concentration, you get the POH. And if you take the negative log of 10 to the negative 14, you get 14. So the pH plus the POH is equal to 14. So if I subtract the POH from 14, I can get the pH. All right, calculate the percent ionization of hydrozoic acid in solutions of each of the following concentrations. The Ka is given in Appendix D. Okay, so we got a 0.4 molar concentration, a 0.1 molar concentration, a 0.04 molar concentration. So the concentrations keep getting lower and lower. So what effect does that have in percent ionization? So if I'm going to figure out percent ionization, I need to know how much this acid ionizes, right? So for every X amount of hydrozoic acid I lose, I make X amount of H plus, X amount of the conjugate base. I plug these into the law of mass action, solve for X. Again, the Ka is so small I can ignore the decrease in concentration of hydrozoic acid. And X is the conjugate base concentration. X minus, X is the conjugate base concentration. So when I'm dealing with percent ionization, I compare that conjugate base concentration to the original concentration of the acid, right? Multiply by 100 to get a percentage. So with this concentration, right, this high concentration, I get a percent ionization of 0.11%. All right, so lowering the concentration, what effect does that have on percent ionization? So I'm losing X. Is X greater or less? Well, let's figure it out. If it's a lower concentration, all of a sudden X is getting more and more significant, right? With the smaller the concentration, X is having more of a magnitude in terms of how much I'm losing. If I lose anything with a very dilute solution, it's something. So when I plug this in, right, when I solve for X, and I plug in how much I lost compared to my original concentration, it's more significant, right? I get a higher percent ionization, right, 0.34%. And when I give it more dilute, again, X gets more and more significant, the more dilute the solution. So much so, if we're not careful, we'll have to solve for a quadratic when we solve for this thing, right? I can't make the assumption that X is inconsequential to the original concentration. So as long as the concentration is high enough, this holds true. When I solve for X and plug it into the formula for percent ionization, the trend follows, right? The percent ionization goes up, the more dilute the solution, right? There's more space now, actually, for this ionization to occur, right? There's more room for it to break apart. Less contact between the H plus ion and the conjugate base to reform the acid. So the more dilute the solution, the more this acid is actually going to break up. Write the chemical equation in Kb expression for the reaction of each of the following bases with water. Dimethylamine, carbonate ion, formate ion. Okay, when you write a Ka expression, it's easy to use, or easier to use, the Arrhenius definition, right? The acid breaking apart into its conjugate base and H plus ion. You leave water out of it because it doesn't appear in the equilibrium expression. Well, that's harder to do with a Kb expression because we need water to act like a Bronsted acid, right, to protonate the base. So this is the Kb expression for when dimethylamine interacts with water. Water protonates dimethylamine to make a conjugate acid, and hydroxide ion is the conjugate base of water. So if I'm going to write the equilibrium expression, I leave water out. Right, water is a liquid. Only things that are aqueous appear in the equilibrium expression. So proximal reactants raise the stoichiometric coefficients. This would be the Kb expression for when water protonates carbonate to form hydrogen carbonate and hydroxide. Right, hydroxide again being the conjugate base of water when it acts like an acid. This would be the Kb expression. And this is the Kb expression for formate ion. And this is the equilibrium expression. Calculate the molar concentration of hydroxide ions in a 0.724 molar solution of hypobromite with a Kb value of 4 times 10 to the negative 6. What is the pH of this solution? All right, so this is the Kb expression for hypobromite reacting with water to make hypobromous acid and hydroxide. If we start out with a 0.724 molar concentration of hypobromite, we're going to lose X amount of that to make X amount of hypobromous acid and X amount of hydroxide. We plug these equilibrium concentrations into the law of mass action, and we solve for X again, right? Kb value is small here. We can ignore the change in the initial concentration. Solve for X. X is equal to the hydroxide concentration. So if I take the negative log of the OH concentration, I can get the POH. And since the POH plus the pH is equal to 14, I can subtract that POH from 14 and get the pH. See how easy it is. Given that the Ka for acetic acid is 1.8 times 10 to the minus 5, and that hypochlorous acid is 3.0 times 10 to the negative 8, which is the stronger acid? Okay. The stronger the acid, the bigger the Ka value, right? The more the ionization. So acetic acid is the stronger acid. B, which is the stronger base, acetate ion or hypochlorite. All right, the relationship between an acid and its conjugate base is an inverse one. The stronger the acid, right, the easier it is to take the H off, the weaker the base, the harder it is to put the H back on. So it's an inverse relationship between the Ka value for a weak acid and the Kb value for its conjugate base. As the Ka gets bigger, the Kb's got to get stronger if it's going to be equal to Kw, which is a constant, right? 10 to the minus 14. So inverse relationship. Large Ka value, small Kb value. So the stronger acid here is hypochlorite, right? It's the weaker acid, therefore its conjugate base is the stronger one. Take the Ka value, divide it into 10 to the minus 14 to get the Kb value, if you didn't see we did mathematically here. All right, so salts. Predict whether the aqueous solution for the following compounds is acidic, basic, or neutral. All right, when you have an ionic compound, you got to ask yourself the question, what kind of acid-base reaction could have formed it? So with the case of ammonium bromide, if I react ammonia with hydrobromic acid, I get this ionic compound. Ammonia is a weak base, therefore its conjugate acid is significant, right? So there's a Ka value for ammonium ion. So if I put ammonium bromide in water, it's the ammonium ion that's going to produce H plus ion. Bromide is the conjugate base of hydrobromic acid, which is a strong acid. Therefore, bromide is a non-base, a nothing base. Same with chloride ion, right? If I have iron 3 chloride, the chloride ion is a spectator here. There's no value in terms of reacting with water to produce hydroxide. Now, the iron 3, on the other hand, will hydrate with water, right? So if you have highly charged cations, water molecules covalently bond, right, in a Lewis acid-base reaction to form a hydrate. The more charged that cation is, the more it pulls electrons towards itself and away from an OH group, which weakens the bond and an H pops off. So you go from this complex ion, right, iron 3 with 6 waters attached, to iron 3 with 5 waters attached, an OH group attached, and a +2 charge. All right, so there's a Ka for highly charged cations. B, sodium ion is a cation that would accompany sodium hydroxide, a soluble ion compound. Sodium ion has no hydrolytic value, but carbonate does. All right, carbonate is the conjugate base of hydrogen carbonate, which is itself a base. So there's a pretty large Kb value for carbonate. So it'll react with water, right? Water will act like the acid, protonate, carbonate to form hydrogen carbonate and hydroxide. D, potassium ion comes from potassium hydroxide. Perchlorate comes from perchloric acid, a strong acid. So if you put this ionic compound in water, nothing's going to happen. Potassium ion won't react with the water, and perchlorate is the conjugate of a strong acid, so nothing. Sodium with this H anion. All right, so I guess technically that H could come off, right? And give you a Ka value, right? Break apart to form H+. Depends where the H is attached to. You could also put an H back on this thing. I'm assuming these H's are attached to oxygens, all right? So you got a double bonded oxygen in here somewhere. So it's going to act like an acid or act like a base. This is when you're called being amphoteric. And it'll depend. Is this a better acid than it is a base, right? A better H giver than it is an H taker. And that'll depend on the magnitude of the Ka or the Kb value. So if this is going to act like an acid, the Ka value for it would have to be bigger than its Kb value, and vice versa.